recording. Here we go. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. When you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. So today we're going to move on to section 11.2. But before we do, here comes Greg. Before we do, are there any questions from 11.1?
No, I don't have any. I didn't have any either.
Okay, Greg?
No, I don't have any.
All right, so then we'll go on to 11.2. And we've got a lot to talk about today. So here we go. Now, we've talked about in the past the idea of a function. And we said that in a function, for each input, there is exactly one output. One input cannot go to more than one output, but several inputs can go to the same output. So just like one person only has one birthday, several people can have the same birthday. One person can't have several birthdays. In terms of graphs of a function, here's a lovely looking graph, there's something called the vertical line test. So for instance, if I want to look at that, that linear equation, the graph, it passes the vertical line test, okay? Or if I want to look at this graph, again, it passes the vertical line test, so it's a function. But if I have something like this, where it fails the vertical line test, it's not a function because for one input, you've got two outputs. So that's not a function. Now, today we're going to look at one-to-one functions. One-to-one functions. A one-to-one function, not only is it a function where each input goes to exactly one output, but also each output comes from exactly one input. So you can't have several inputs going to the same output. That's a function, but it's not a one-to-one function. So let's look at some examples here. Let's say we've got 1, 2, 3, 4, 5, 6. 1 goes to 4, 2 goes to 5, and 3 goes to 6. That's a one-to-one function mapping, okay? Let's say we've got 1, 2, 3, 2, 7. 1 goes to 2, 2 goes to 2, and 3 goes to 7. That is a function, but it's not one-to-one because you've got two different inputs going to the same output. All right, now, yes, the graph of a one-to-one function, for instance, this linear equation, not only does it pass the vertical line test, but it also passes a horizontal line test. So if you're looking at a graph that's a one-to-one function, you can cut through it with vertical lines and never have any one line cut to the graph more than once. You can cut through it with horizontal lines and have the same results. Okay, so what about a parabola? Well, that is a function, but it's not a one-to-one function. Okay, linear equations, well, all of them are one-to-one functions except a horizontal line. Well, let's do this. If you've got a horizontal line, that's not a one-to-one function because it fails the horizontal line test. And if you've got a vertical line, that's not a one-to-one function. That's not even a function. But other than the vertical lines and the horizontal lines, all other linear equations are functions and they are one-to-one functions. Okay, any questions about that yet?
No.
All right. Let's talk about how to, oh, here's what I want to say. If you have a one-to-one function, that function has what is called an inverse function. The best example I can give is this. If you go by the bank on Nob Hill and 31st Avenue, there's a sign, and it doesn't mean that you have to have seen it, but it gives the time, and then it gives the temperature in Fahrenheit, and then I think it gives the temperature in Celsius, and then it gives the time, and then it gives the temperature in Fahrenheit and the temperature in Celsius. We could take a formula that converts from Fahrenheit to Celsius, and we can take that Celsius formula and go back to Fahrenheit. So it's like one of them goes to the other one gets you back again. So if you have a function, it will take you to its inverse will take you back to the original function. Anyway, we'll talk more about that as we go on. There is a process by which we can take a one-to-one function and algebraically find its inverse. Now, earlier I said that all linear equations other than horizontal or vertical lines were one-to-one functions. Let's take, for example, f of x equals 5x minus 1. So the graph of that is a straight line going through what a y-intercept of -1 and a slope of 5. It is a one-to-one function. Okay, now we are going to find its inverse. The first step we're going to do is we're going to replace the f of x function notation with just a plain old ordinary y. Okay, so f of x gets changed into y. That's step 1. Step 2, we are going to interchange all the x's with all of the y's. So now our equation becomes x equals 5y minus 1. So again, step 2, change all the x's to y's, change all the y's to x's. At this point, the equation that we are dealing with is in fact the inverse function, but we're going to go on and now we're going to solve it for y. So to do that, I'm going to add 1 to both sides of the equation. And then I'm going to divide both sides of the equation by 5. I'm going to rewrite that putting y on the left side. I don't have to, but I just prefer to have my y value on the left. So that's not really a step. That's just my own thing. So that was step 3, solving the equation for y. Step 4 is replacing y with the inverse function notation. So now y becomes f inverse of x. Now, that looks like f to the -1 power, which would then be 1 over f, and that's not the case. This notation means that it's the inverse of f. So this is the f inverse function, okay? So f inverse of x equals x plus 1 divided by 5. So again, the 4 steps. Step number 1, we replaced f of x with y. Step number 2, we swapped all the x's and y's around. Step number 3, we solved for y. Step number 4, we replaced y with f inverse of x function notation. All right. Any questions about that particular problem? Okay. What I want to do now, I want to rewrite those 2 functions. Let's see here, what was it? It was x plus 1 over 5. And I want to find some table values of these 2 functions. Okay. See if I can write this correctly. Minus 1. Okay. So we're going to find some ordered pairs. Oh, how about -3, -2, -1, 0, 1, and 2? Okay. All right. So if x is -3, what would f of -3 equal? That would be 5 times -3 minus 1, which is -15 minus 1, or -16, right? Okay. If x is -2, f of -2 would be 5 times -2 minus 1, -10 minus 1, -11. F of -1 would be 5 times -1 minus 1, which is what? -6. F of 0 would be -1. F of 1 is 4, and f of 2 is 9. Are you okay with those values?
Yes.
Okay.
Yeah.
Now, let's go over here, and let's find some table values over here. And for x's, I want to just pick some random numbers. How about -16, -11, -6, -1, 4, and 9? Let's just go with those, okay? All right. I just kind of pulled those out of thin air. So, first liar hasn't got a chance. If x is -16, we would get -16 plus 1 over 5, which is -15 over 5, which is -3, right?
Yes.
Okay. If x is -11, we'd get -11 plus 1 over 5, which is -10 over 5, which is -2. If x is -6, we'd get -6 plus 1 over 5, which is -5 over 5, which is -1. Let me ask you this. What do you think is going to go right here?
0,
And here?
1,
And here?
2.
Good. You've discovered the secret. I lied. I didn't just randomly pick those values. Those are what? Those are the y values over here. Well, the x values of the original function become the y values of the inverse. The y values of the original become the x values of the inverse. Or let me say that a different way. The domain of the original function becomes the range of the inverse. The range of the original becomes the domain of the inverse. So if you have a one-to-one function and you've got some ordered pairs that are solutions, you could take all those ordered pairs and switch the x's and y's and get ordered pairs for the inverse. Think about it. When we went through this process of finding the inverse, we interchanged the x's and y's, right? So when you're getting table values for a function or a graph, your ordered pairs for the inverse are going to just be inversed, so to speak. Okay? Any questions about that?
No.
No.
All right. Let's see here. Let's do another one. And this time I'm going to switch to the other screen. So we'll get rid of that and open up the graphing screen. Okay. And let's see here. I guess we're being environmentally good today. We're going green. I'm going to switch that. Okay. So let's take another equation. Let's take this. F of x equals 2x plus 6 all over 3. My graph is giving me problems. It's not behaving. Let's see if we can get things to be straightened out here. Nope, it's not cooperating. This is not good. Earlier, things were working fine, but we'll see what happens. Okay. Every once in a while, it acts up. And today, it chooses to act up. Okay. 2x plus 6 over 3. Okay. Let's find some ordered pairs and graph this thing. Okay. So we're going to make a table. Let's find 3 ordered pairs. How about x is 0? X is 3, and x is 6. Now I know that 3 doesn't look like a 3. I'll see if I can get it to work. I have to reboot my computer to make this thing fixed, and if I do that, I lose all of you, so I'm just going to live with this miserable thing. We'll see if I can do it okay. Well, that's supposed to be a 3. Maybe we'll use, well, okay. I'm going to try once more. Well, that kind of looks like a 3, doesn't it? Okay. What's that?
It looks like a 3.
Good. I know. Sorry, this is frustrating for me. I always check ahead of time to make sure things are working, and 2 hours ago things were working, but now they aren't. Okay, if x is 0, what's 2 times 0?
0.
Plus 6.
6.
6. 6 divided by 3 is
2.
2.
okay. Maybe if I do it a piece at a time. If x is 3, what's 2 times 3?
6.
What's 6 plus 6?
12.
What's 12 divided by 3?
4.
Okay, I know this is pathetic. If x is 6, what's 2 times 6?
12.
Plus 6
18.
divided by 3?
6.
6. Go really slowly, maybe it works. All right, so now I'm going to plot those points. So let's see, 0, 2, it's right there, right? 3, 4 is right there. And 6, I guess I should put a scale on here, though who knows whether that's going to work nicely. Well, I guess it's behaving at the moment. 6, 6 is right there. Okay. Did those 3 points line up?
Yes.
Yes, they do. Okay. All right. So there is a function. Would you agree that it's 1-to-1?
Yes.
Yeah.
Okay, let's find its inverse. All right. So we're going to take the original function. We're going to replace f of x with y. So now we get y equals 2x plus 6 all over 3. Maybe this is just God's way of saying you need to slow down. Okay. Now we're going to interchange x and y. So all my y's become x's and all my x's become y's. So x equals 2. I know this is painful for you. It's painful for me too. 2y plus 6 over 3. Okay, We all right with that?
Yes.
Yes.
Now we're going to solve for y. So first of all, let's clear the fraction. We'll multiply both sides by 3. I had to choose 3. I think 3 is one of the worst numbers to try and do for whatever reason. It's like it's taking forever to graph. Oh, well. All right. So now on the left, I get 3x equals 2. I'm going to switch to the other screen as soon as I can. 2y plus 6. Okay. So what would you do next to solve for y?
Subtract 6 from both sides.
Okay, subtract 6 from both sides. Apparently it likes 6s, it just doesn't like 3s. So now I get 3 x minus 6 equals 2y. And then finally,
Divide both sides by 2.
divide both sides by 2. So y equals 3 halves three x minus 3. Okay, you see where I got this? Oh, 3 halves x, sorry. You see where I got that? Splitting this up into 2 separate fractions.
Yes.
And then finally, f inverse of x would be 3 halves x minus 3. Okay? Boy, if anybody's having trouble keeping up with me taking notes, you must be really slow today, huh?
I have a question.
Yeah.
So you put f inverse of x, but is it always going to be -1?
Well, that's just a notation.
Oh, okay.
That's, yeah, that -1 means, so this says we're dealing with f inverse. That's the notation.
Okay. I was just making sure.
Yeah, it doesn't mean reciprocal or -1. It just means, oh, this is the inverse of that. That's just the way we label it.
All
Okay.
right. Thanks.
All right. Now, would you agree, based on an example we did a little while ago, that this is an ordered pair of that equation?
Yes.
And that's an ordered pair of that equation?
Yes.
And that's an ordered pair of that equation. So let's graph those points. 2, 0 is right there. 4, 3 is right there. And 6, 6 is right there. And let's plot. Let's see here. Well, this thing's supposed to go all the way across there. So is that. Okay, so let's draw that line. Okay. Oops. I think what happens is that when it doesn't change into the drawing mode, it stays in that straight line mode. And that's what I get all this mess. People are going to look at this and think, what drugs was he on when he did this lesson? None, just water. Okay. So we now have f of x and f inverse of x, okay? If we draw the line, and let's see here, let's do this with red, and this is my attempt at drawing a dotted line. Actually, you know what? Wait, I just remember there's an easier way to do this. Okay. I'm going to draw the line y equals x. Okay. Now, I'm going to erase little pieces of it. There we go. Okay. Can you see that f of x and this mess down here that's supposed to be f inverse of x are symmetric with each other about the line y equals x?
Yes.
Okay, good. So here's what we can conclude so far. If a function is one-to-one, it has an inverse. There's a four-step process we can go through to find that inverse. The ordered pairs that are solutions to f of x, if you take the x's and y's and you switch them around, you get ordered pairs that are solutions to the inverse. If you graph both f of x and f inverse of x on the same graph, those two graphs are symmetric about the line y equals x. So in fact, I could have done this had I chosen to. I could have said, well, let's see here. I could erase all of this and erase, let's see here. Okay, and I could have said, you know what? I can graph f inverse just by looking at the graph of f. I could say, okay, what do we got here? This point is 6, 6. This point is 3, 4. So 4, 3 is right there. I should use a different color. Let's go with blue here. So this point is 4, 3. This is what, 0, 2. So 2 zeros on the graph. This is what, negative 3, 0. So 0, negative 3 is on the graph, et cetera, and then I could get that graph. You see what I'm saying? I should use the straight line on it, but okay. I'm going to go back to the other screen. All right. Hopefully we won't have troubles with this one. Usually when one messes up, the other one messes up, but so far things were okay. We'll see what's happening. All right. Confuse people here. Let's take a look at another equation. Let's take f of x equals 2x plus 9, and let's take its inverse, which is x minus 9 over 2. X minus 9. Say one thing and write another. That's not very helpful. That's the other thing. I hate when this thing does this because it gets me all distracted, and I quit making excuses. Just do it. Okay. Now, here we have a scenario where they are claiming that f of x and f inverse of x, that those are in fact inverses of each other, okay? One of the ways we can determine whether two functions are inverses of each other are to use composition of functions in both directions. If they are inverses of each other, in both cases, we will get the same answer, and that is x. Remember that yesterday I said in general composition was not commutative, but in this case, it should be. So what we're going to do, we're going to take f composed with f inverse of x, and we're going to figure out what that is. Okay, so that would be f of f inverse of x, which would be f of x minus 9 over 2. Okay. So far, so good?
Yes.
Yes.
That's going to be smart. So I'm going to take all of that and put it right there. So that's going to be 2 times the quantity x minus 9 over 2 plus 9. Simplifying that, it's going to be x minus 9 plus 9, which is going to be x. So far, so good. Remember I
Yes.
said, if they're inverses, when we compose them both directions, we should get x as the answer. Now let's do the second one. F inverse composed with f of x. So that would be f inverse of f of x, which would be f inverse of 2x plus 9, which would be 2x plus 9 minus 9 over 2, because I'm taking all of this and putting it right there. Okay. Simplifying this, that would be 2x over 2, which would simplify down to x. So we can conclude based on composition that in fact these two functions are inverses of each other. Okay. So if we have a one-to-one function, there's a 4-step process by which we can find its inverse. And I could go through that to get there, but they already said they were inverses. If you graph those two lines, they'd be symmetric about the line y equals x. Ordered pairs from one, reversed, would be ordered pairs to the other. When you compose them in both directions, you get an answer of x. Okay. Now, let's take a look at this problem. F of x equals x squared plus 1. And then in parentheses, it says x greater than or equal to 0. All right. So let's see if we can find the inverse of this function. So step number 1, replace f of x with y. Okay. Step number 2, interchange x and y. Oh, I screwed up, didn't I? I'm looking at that going, no, something's wrong there. Yeah. This should be what? X equals y squared. You're not interchanging x squared and y, you're interchanging x and y. So y becomes x and x squared becomes y squared, okay? Sorry about that. Again, my focus is just kind of blown here. Subtract 1 from both sides, and I'm going to get y squared equals x minus 1. Are you okay with that so far?
Yes.
Yeah.
Yes.
So what would you do now to solve for y?
Take the square root.
Right. And then finally, change it into F inverse notation, okay? Now, ordinarily, I would go back to the graphing screen but I'm thinking that's probably a bad idea the way things are going today. So I'm just going to kind of freehand the graph here. So bear with me. Let's see here. Okay, I admit I'm cheating. I'm using a ruler. The graph of f of x equals x squared plus 1. Wouldn't that be a parabola y equals x squared, but moved up 1 unit? So basically it would look like, oops, that. Okay, you all right with that?
Yes.
So that's the graph of, let's see if I can make a better drawing there. Probably not. That's the graph of y equals x squared plus 1. Is that a one-to-one function?
No,
No, it's not, is it?
because it doesn't pass the vertical. It passes the vertical, but doesn't pass the horizontal.
Right. But you know what? I've completely and on purpose ignored this. That is a restriction imposed on f of x, which will turn it into a one-to-one function. That says that x has to be greater than or equal to 0. Well, in that case, our graph, come on, eraser. Nope. The graph would look like that, wouldn't it? If we restricted x to being just greater than or equal to 0. Ah, is that one-to-one?
Yes.
Okay, we're back in business. Now, let's graph this. Okay, now I'm not going to take a lot of time to do this because to prove my point, I don't need to do that. But if I graph that, I would get the plus would look like this, and the minus would look like this. Okay, is that a one-to-one function?
No.
No. Well, a function and its inverse are both supposed to be one-to-one, but here's the deal, okay? This was a restriction on the domain of f of x, right? It said that x had to be greater than or equal to 0. Way back earlier, I said that the domain of a function is the range of the inverse, and the range of a function is the domain of the inverse. Do you remember that?
Yes.
Okay, so if the domain of the function has that restriction, then the range of the inverse has that restriction, which means y has to be greater than or equal to 0, which means this piece, which is the minus, doesn't exist. Now we have our symmetry about the line y equals x. We've got our two pieces of graphs, and they are both one-to-one functions. So do you see how that worked?
Yes, I did.
So we took a function that was not one-to-one. We restricted the domain to turn it into a one-to-one function, this piece. Consequently, we also have a restriction on the range of its inverse, which gives us the correct piece for the inverse function. Okay, so if you have a function, it passes the vertical line test. If you have a one-to-one function, it passes the vertical line and the horizontal line test. If you have a one-to-one function, there is an inverse function, which is also one-to-one. To get from a one-to-one function to the inverse function, there's a four-step process. Replace f of x with y, solve for y. No, excuse me, I messed that up. Replace f of x with y, interchange x and y, solve for y, rewrite y using f inverse of x, okay? The two graphs of the two inverse functions will be symmetric about the line y equals x. If you compose those two functions in either direction, you should get x as an answer. All righty. So there you have it for section 11.2. I'm going to stop the recording.